All right, good. Because I wasn't going to answer them anyways. So the next two topics are the two coolest topics in this whole class. And of those two, this is probably the one that's most, that's going to be useful in the most cases. So the new topic is two-dimensional linkages. And linkages are collections of rigid bodies connected by joints. So this is an example of a 2D linkage. The 2D just means that everything moves in the plane. So let's say that there are pin joints connecting all these things. And then there's some known force vector applied here. And let's say that you apply some known couple here, 100 Newton meters or something. What are the angular accelerations of the individual bodies? And so you might imagine, linkages are the basis for machines, robotics, calculations in biomechanics, and probably a bunch of other stuff. So yeah, this is a super useful topic. The difference, what do you call, so that's a linkage. What would you call it if I put, let's say, another bar here that connected it there, and now this thing couldn't move? A bar connecting this joint to the wall, and now you could apply all these loads and that thing would be stationary. Yep. A truss is a kind of structure. So generally structures. So if it's a static thing, it's a structure. And if it moves, it's a linkage.
Are those members?
Yes, that's right. And so let me give you sort of the overall process for a linkage, and then we'll just do a couple of examples. So first, number each member in the linkage, just for bookkeeping. And then second, one by one, isolate the members in the linkage and use Newton's laws. If the member has a fixed point, If it has a fixed point, do you use Newton's second law or not? Right, so if it has a fixed point, you're not going to use Newton's second law. And so the rotational Newton's second law gives one equation. If the member has no fixed point, then Newton's second law and the moment equation you get two equations for Newton's second law, one for rotational, and so three equations. Yep. Okay, so our inertial coordinate system is fixed to the wall. It's stationary compared to the wall. So this and this both have fixed points. Those don't go anywhere in the coordinate system. This and this are fixed to, they're attached to other members, but those points move as this thing rotates up and down. Okay, so the question is it fixed in the inertial coordinate system? When you're done with all the members, so when you've done every member, you think you have enough equations to solve? How would you know? I'm going to tell you. No, you don't have enough. You don't have enough equations. And so the extra equations come from joint constraints. Okay, so now you've used Newton's laws for every member. You still have more variables than equations. And the last step is at each joint that's not fixed, so that's what we were just talking about. So in the example up here, two of these joints are fixed points. We don't have to worry about those. But two of them are not fixed. And at those two that are not fixed, the restriction that we have to say basically is there's a point on this member that, that joint is a point on this member, okay? And that joint is a point on this member. And the acceleration of the point on this member has to be equal to the acceleration of the point on that member. Just saying that those members can't fly apart at the joint, okay? They have to stay in the same place. So the acceleration according to one attached member must equal the acceleration according to the other attached member. And these accelerations come from the watermelon equation and relative motion. Okay, so like for example, you'd get an equation that says like the acceleration of the center of mass of member 2 plus alpha 2 cross some r, let's say this is a joint P, say 2P. These don't really mean anything right now. I'm just saying that, so according to member 2 now, I'm writing the acceleration of that point at the joint. And then we have to set that equal to the acceleration of that point according to member 1. Okay, so how many useful equations would we get out of this at one joint? It's a two-dimensional problem, so these accelerations are in 2D, so each one of these would give 2 more constraint equations. And one more thing, I mean, we're going to go through a bunch of examples, but how would it be the case that, so I'm saying, like, let's say that in this example, I'm doing the constraint for this joint here, okay? And so I'm saying the acceleration of that point according to this member is equal to the acceleration of that point according to this member. Why would it ever be the case that so on this side, I'm using obviously circular motion, but also relative motion to calculate the acceleration of that point, okay? And over here, I'm using circular motion, but no relative motion. Why would it be the case that on one, I would use relative motion? Yeah. Yep, that's exactly right. So if you're doing, so if you're calculating the constraint equation at this point, in order to calculate the acceleration of that point according to this member, you don't need relative motion because it's moving around this fixed point, okay? So you don't need relative motion. For this one, neither of those 2 points is fixed. Nothing on there is fixed that we know of. So you need to calculate the acceleration of the center of mass and then use relative motion to add on the circular motion part. Okay, so yeah, the 2 things you're going to use are circular motion and relative motion. You won't always need relative motion. Yes, that's right, exactly. So relative motion, this you're only going to need for members with no fixed point. Okay. Here's a bookkeeping rule. assume that the joint itself, usually we'll be talking about pin joints, so the pin itself. Assume the joint itself is part of the lowest numbered member that it connects. Okay, so let me describe what I mean here. This is the same idea that the people who took statics from me, this is how we did it in statics. And let's say that this one that has a fixed point is member 1, and this one with no fixed point is member 2. Okay. Then this joint connects member 1 and member 2. Okay, so we're going to assume that the pin itself is part of member 1. Okay, and that means that if you had forces applied to the pin, which happens in these a lot, you treat that as that external force is something that's applied to member 1, but not applied to member 2. Okay, it's just a bookkeeping thing. You could use the exact opposite rule of that. The only thing you can't do is if you have a 500 Newton force acting at that pin, treat it like it's 500 Newtons acting on this one and 500 Newtons acting on this one. Okay. All right, so let's start out with sort of, this is the kind of simple calculation that a lot of biomechanics studies start with. So let's say there's a hinge on the ground and a member with a 45-degree angle. So say that angle is 45 degrees, and then a pin joint connects that member to another one that's perpendicular to it. Let's call these joints A, B, and C. And this angle is 45 degrees, and this is a right angle. And I'll call this member 1 and this member 2. And let's say that the external load that's applied is 100 newtons this way. Okay, so if you made the lengths and masses of these things, relate to a leg, and maybe you put a extra mass up on top to show, so that you can sort of simulate the body being there. This might be sort of a simulation of the kind that you'd want to calculate, like the kind of joint forces that would be caused by this injury or whatever. Okay, so let's say that the length of both of these is 1 meter. And let's say the mass of both of them is 5 kilograms. And let's say at this instant, omega 1 and omega 2 are both negative 10 radians per second. And we want to calculate, well, let's start by just calculating the angular accelerations of both of these members. Okay, so first of all, what's happening with that? Let's think about what's happening with those angular velocities. So -10 means those are both rotating clockwise. Does it make sense that these are rotating clockwise when the only force, well, there's a weight force, I guess, but, and then this force is pushing this way? It does. That's kind of like a trick question, misleading question in a way, because any velocities, so Newton's laws say that forces and moments relate to accelerations and angular accelerations. They don't have any relationship to velocities. Velocities you can think of as being caused by integrating the accelerations through time up until that instant. Okay, but what happens, the loads that are applied at that instant don't have any instantaneous effect on the velocity. Okay, so basically what this means, if these are both rotating clockwise, it means that up until this instant, loads have been applied that made them both rotate clockwise. And then right at this instant, maybe this load got switched out for this one. Okay. And so now physically, what does it mean that these both have the same angular velocity clockwise? What's this doing? Here's the distinction that I want to make. I think probably to a lot of people, you would think, okay, member 1 has an angular velocity of 10 radians per second clockwise, and that's right. And then a lot of people would think member 2 is rotating clockwise at 10. So the whole thing's rotating down, and the angle between these is getting bigger. But that's not what happens. That angular velocity, every angular velocity you get for a body is relative to the coordinate system, not to what it's attached to. Okay, so that omega-2 doesn't have anything to do with this. And so in other words, the angle between those is actually staying the same. Okay, and the whole thing is just tipping down that way. So remember, angular velocities and accelerations are given with respect to the coordinate system. So this has two members. They're already numbered. And so now we're just going to isolate the individual members and go through the rigid body process for each one. So I'll start with member 1. And we'll just go through the steps for a rigid body. Does member 1 have a fixed point? Yep. And so the about point is the joint A. And so step 2, we can calculate the mass moment of inertia. So I sub A is equal to 1/12 times 5 kilograms times the length squared. But that's the mass moment of inertia about the center of mass. So now we need the parallel axis theorem. So that's plus 5. And then what's the distance? 0.5. Yep, it's the distance from the center of mass to the about point. And so 0.5 squared. And so 5/12 plus 1.25. What is it? 1. Okay, kilograms meters squared. And now free body diagram. There's a weight force acting at the center of mass. That's 5 times 9.81, so 49.05. The pin joint applies an unknown force vector. I'll call that RA. And then the pin at the top applies an unknown force vector from member 2. So I'm going to call that the force on 1 by 2. And there's one more thing. Since we always assume that the pin is connected to the lowest numbered member, that 100 Newton force is applied to member 1. And so now rho, force, moment. So first I'll do the force RA. That is the about point. So rho vector is 0. The force vector is RAX, RAY, and the cross product is 0. And then the weight force, the rho vector is 0.5 times cosine and sine of 45 degrees. So that's 0.3535, 0.3535. The force vector is 0, negative 49.05. And what's the cross product?
Minus 17.34.
Minus 17.34. And then the force F12. The rho vector is 0.7071, 0.7071. The force is F12x, F12y. And so the cross product is 0.7071 F12y minus 0.7071 F12x. That's not a vector, that's just, I was running out of room. And then there's one more force, the 100 Newton force. It has the same rho vector as F12. The force vector is negative 100, 0. And so the cross product is positive 70.71. So Newton's second law says RAX, RAY plus 0, negative 49. Oh, we don't need this. Step 5. We don't need Newton's second law. Step 6, rotational Newton's second law. So that says negative 17.34 minus 0.7071 F12X plus 0.7071 F12Y plus 70.71 is equal to the mass moment of inertia, 1.6 repeating, times the angular acceleration of body 1. Okay, so we only have one useful equation from this, and that's always the case for the bodies with fixed points. So I'll set that aside as equation 1 star. I'm going to move all the constants over to the right side. So we have negative 0.7071 F12X plus 0.7071 F12Y minus 1.6 repeating alpha 1 is equal to, what's 70.71 minus 17.34? 53.37 negative. And we have one equation, 3 variables, so we can't solve it yet. So we're just setting that aside for our big system. Now we'll go to member 2. Okay, so member 2 is the top member. Does that have a fixed point? No. So the about point is the center of mass. And so the mass moment of inertia, I guess I'll just, I'll call this like just the mass moment of inertia for body 2 is just 1/12 times the mass times the length squared. And I think that's 0.416 repeating. And now a free body diagram. There's a weight force of 49.05. There's no force at the top. At the bottom, member 2 is connected to member 1. There's the force on 2 by 1. But if we call it F21, then we've introduced new variables we don't need to introduce. And we definitely can't do that. So we need to use Newton's third law. And this is equal to negative F12. And now that's not introducing any new variables. And that 100 Newton force doesn't apply here because it's applied to the pin, which we said was connected to member 1. We're treating it as part of member 1. Force, moment. So first, I'll do the weight force. That's at our about point. So the row vector is 0. The force is 0, negative 49.05. No moment. And then the second one is negative F12. The row vector there is 0.3535. negative 0.3535. The force vector is negative F12x, negative F12y. And the cross product is negative 0.3535 F12y minus 0.3535 F12. Do we need Newton's second law for this one? Yeah, no fixed point, so we need it. So we have 0, negative 49.05 plus negative F12x, negative F12y is equal to the mass of the body times the acceleration of its center of mass. And we don't know anything about that. So these are new variables. I'll call it A2, X and Y. So remember, this is the acceleration of the center of mass of body 2. And then the moment equation says negative 0.3535 F12x minus 0.3535 F12y is equal to 0.416 repeating times alpha 2. And so this one we got 3 useful equations. For our system of equations, these are equations 2, 3, and 4. So I'll call this one 2 star. Says negative F12x minus 5A2x is equal to 0. Equation 3 star says negative F12y minus 5A2y is equal to 49.05. And then equation 4 star says negative 0.3535 F12x minus 0.3535 F12y minus 0.416 repeating alpha 2 is equal to 0. So now we have 4 equations. And how many variables do we have? Well, here is something you have to be careful about. If you look at the free body diagrams, you would get the wrong number of force variables, because look at what happened with number 1. We had 2 unknown force vectors, and they both appeared in the table. But since this one has a fixed point, we didn't use Newton's second law. And so even though this appears in the free body diagram, it's not in our system of equations. We could solve for it later if we want. But from our first equation, we don't have any RA, and we also don't have any acceleration. All we have is the force vector F12 and the angular acceleration alpha. Okay, so we have 3 variables in the first equation. And then in the next 3 equations, that's not new, but we do have the acceleration. So let's start writing these down. So how many variables do we have? We have F12, we have alpha 1. Those are from the first equation. And now from the next set of 3 equations, we have the acceleration of the center of mass of 2. And we have the angular acceleration of 2. So 4 equations, 6 variables. Well, the way it's always going to work out is how many joint constraint equations are available to us. We never have to do joint constraints at ones that are fixed. So even though there's 2 joints, this is the only one that's useful to us. Okay. And so the difference between our number of variables and our number of equations just exactly matches the number of constraint equations. Okay. So we need 2 more equations, 2 constraint equations. And we'll get those from joint B. And so this constraint equation is going to say basically the acceleration of B according to member 1 has to be equal to the acceleration of B according to member 2. Okay, so first member 1. This is just, so if we're calculating the acceleration of this point using this body, that's just a simple circular motion because this point is fixed. And so A is fixed, so we don't need relative motion. So the acceleration of the point B, according to member 1, is 0, 0, alpha 1, crossed with the R vector. The R vector goes from the center of the circular motion to the point we care about. So that's the vector from A to B. So that's 0.7071, 0.70710, plus the angular velocity that's given at the start of the problem. So that's 0, 0, negative 10, crossed with the quantity 0, 0, negative 10, cross 0.7071, 0.70710. So what do we get here? This one is going to be negative 70.71, negative 70.710. And this one is going to be minus 0.70 0.71 alpha 1 plus 0.7071 alpha 1, and then 0. So this whole thing comes out to be, this was round off here, 70.71. Okay, so negative 0.7071 alpha 1 minus 70.71, and then 0.7071 alpha 1 minus 70.71, and then 0 for z. Any questions about that one? Yep.
Can you just step back to the fact that acceleration would be about 1, I think, but acceleration would be about 2?
Yeah.
Okay. I'm not seeing that.
So we're just saying that, so this joint B is a point on member 2 and it's a point on member 1, right? And so we're just saying that if we calculate the acceleration of that point on member 1 and calculate the acceleration of that point on member 2,
Okay.
those have to be the same. If they're not the same, then it's flying apart, you know? So we're restricting it to move together.
The angle between those two not changing.
The angular,
90s.
according to the velocities, it's staying the same. We will see that there are different angular accelerations, I think. I don't really remember for sure. But, I mean, you can imagine, like, what's going to, so velocity-wise, it's staying the same. But acceleration-wise, this force is going to make this start to, you know, open or whatever. The angle's going to start getting bigger. So they're not going to have the same angular accelerations. It's like if you're running and someone smashes into your knees do that. That's a rude thing to do, though. I'll tell you that. Okay. So next time, okay, this is as simple as a linkage problem can get. I can't think of a simpler one than this, and so these take a long time. Eventually, if you're doing this kind of work, you're writing software that does this stuff. You're not doing these calculations by hand. But next time we'll do member 2, and then we'll solve this system. Okay, that's all. You don't think so? Okay. Well, we're in the middle, towards the end of an example problem. So here's the example from last time. We had a hinge on the ground connected to 2 slender rods. I numbered them 1 here and 2 here. The masses are the same. They're each 5 kilograms. The lengths are the same, each 1 meter. the angles are 45 degrees here, and this is a right angle. At this instant, the angular velocities are both the same, negative 10 radians per second. And it's negative, so it's clockwise. They're both the same. And I stressed last time that whenever you're talking about rotational things, you're talking about that rotational quantity relative to the coordinate system, to the ground, not to some body it's connected to. So what that means is both of these are, their orientation is changing at 10 radians per second clockwise. And that means that this thing is just all as a single piece rotating like that. But we don't know what the angular acceleration is. So at this instant, that angle of 90 degrees is staying constant as the thing tips forward. If you think of this as sort of like a simple, as the legs of a person, this person is tipping over onto their face. Unless they have really terrible knee hyperextension and then they're tipping over onto their back. Okay, so, and there's a force. So you're applying a force at the knee of 100 newtons, and we want to see what that does to the accelerations. All right, so we isolated member one. Does member, yes? Nope. That would just be like not enough information. I suppose if you saw that on homework and it didn't say anything, you'd assume that it was 0. But and we isolated member one. Does it have a fixed point? Yes. And so we didn't have to use Newton's second law. So we don't have the acceleration of the center of mass as a variable. And we only use the rotational equation. So we get one good equation for member one. And that equation was negative 0.7071 F12x plus 0.7071 F12y minus 1.6 repeating alpha 1 is equal to negative 53.37. And then we isolated, and that's all we get out of that because we only have the rotational equation because of the fixed point. And then we isolate member two. Does that have a fixed point? No. You might think like, yeah, it's connected to member one, but that point isn't fixed. It can move in space. So we will use a constraint equation for that, but it's not a fixed point. And so we did have to use Newton's second law. And we did have to introduce the acceleration of the center of mass as a variable. And so that gives us three good equations, and those are negative F12x minus 5a 2x component. That's the x component of the acceleration of the center of mass is equal to 0. And then the y component equation is negative F12y minus 5a2y is equal to 49.05. And then the moment equation says negative 0.3535 F12x minus 0.3535 F12y minus 0.416 repeating alpha 2 is equal to 0. And those are our four equations after we're done with Newton's laws.
We have 4 equations, but variables we have 1, 2, 3, 4, 5, 6. And so we need 2 constraint equations. And it turns out it's always going to come out as a perfect match if this goes right between the number of variables that you have above the number of equations. So the number of equations you need and the number of equations that come from the joint constraints. Okay. So the joint constraint we'll call this joint. So let's call that A, B, C. And so our joint constraint is going to be at B. And it's going to say the point B on member 1 has the same acceleration as the point B on member 2. We already did member 1. And we got that the acceleration at that point B was equal to negative 0.7071 alpha 1 minus 70.71 for x, and then positive 0.7071 alpha 1 minus 70.71. Okay, so that's the acceleration vector of the point B on member 1. And now we're going to member 2. Okay, so what's our strategy for expressing the acceleration of B on member 2, given that it doesn't have a fixed point? Member 2 doesn't have a fixed point. Yeah. You use watermelon equation to, so we're going to use 2 things here. First, we're going to express the acceleration, well, use the acceleration of the center of mass of 2. Those are variables already, okay? And then we're going to add to that its relative motion, the acceleration, assuming that the center of mass is fixed, the acceleration of that point B using the watermelon equation. Okay. So you can think of this as, so the acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass of 2, plus the acceleration of the center of mass of 2 relative to the ground. Acceleration of center of mass of 2 relative to the ground. This one is already in our list of variables. That's A2. And this one is just circular motion. So that's alpha cross R plus omega cross quantity omega cross R. Okay, so the acceleration of V, according to member 2, is A2 plus 0, 0, alpha 2, and I'm just using all variables that we've already defined, crossed with the R vector. So if you're using
circular motion, assuming that the center of mass is fixed, the r vector goes from the center of mass to the point B. Okay? So that's 0.5 times cosine and sine of negative 45.
So that's 0.3535, negative 0.3535, and then plus our omega is what was given at the start. So that's 0, 0, negative 10, crossed with the quantity 0, 0, negative 10, cross, same r vector again. This one comes out to be 0.3535 alpha 2 for x, positive 0.3535 alpha 2 for y. And this one, once you multiply it all out, that's just numbers, and it comes out to be negative 35.35 for x, positive 35.35 for y, 0 for z. And so if you add it all together, you get an acceleration of that point B that's equal to, for the x component, a2x plus 0.3535 alpha 2 minus 35.35. That's the x component. And the y component is a2y plus 0.3535 alpha 2 plus 35.35. And then there's no acceleration in z. This is just a planar problem, so I'm going to just leave it to 2. We can only do planar linkages. Why can we only do planar linkages? Well, we can only do planar rigid body problems. So since this is all built around rigid body kinetics, that's a restriction that we just absolutely have. We can only do 2D problems of rigid bodies for now. Okay, so the constraint then says that those accelerations have to be equal. So you can write this out as, I'm probably writing this all out more times than I need to, but at least this first time, I just want to be, clear about what we're doing. So first, on the left side, I have the acceleration of B on member 1. So this is what we got on Wednesday, negative 0.7071 alpha 1 minus 70.71 for x. And then for y, we have positive 0.7071 alpha 1 minus 70.71. And we're setting that equal to what we just calculated, the acceleration of B on member 2. So that's a2x plus 0.3535 alpha 2 minus 35.35. And then the y equation, a2y plus 0.3535 alpha 2 plus 35.35. And that gives us our 2 more equations that we need. We had 2 more variables than we had equations before the constraint. We needed these 2 more equations, and so I'll just rearrange these, put them in a form where we can use reduced row echelon form. And so the first one says negative 0.7071 alpha 1 minus A2x minus 0.3535 alpha 2 is equal to 35.35. And the second one says 0.7071 alpha 1 minus A2y minus 0.3535 alpha 2 is equal to 106.06. We didn't introduce any new variables, so now we have 6 equations and 6 variables. And now we have a system we can solve. Yep. The the left side. Okay, so what I did is, so we're saying that this point, there's a point on member 1 that's at B, okay? And there's a point on member 2 that's at B. And if they're connected by a pin joint, then the accelerations of those 2 points have to be the same. That's what it means to be connected by that pin joint, okay? So first we isolated member 1. We did this on Wednesday, so I didn't do it here. But first we isolated member 1, and since member 1 has a fixed point, all we had to do was use circular motion to figure out the acceleration of that point B on member 1 around the fixed joint. So we got that. And then we went to the second one, which doesn't have a fixed point. And if you don't have a fixed point, you have to express that acceleration in terms of relative motion. Okay, so yeah, that's right. So this one here is just the expression for the acceleration of that point B on member 2. But then once we got that, we just, we did it for member 1, did it for member 2, and set them equal to say their accelerations have to move together because they're locked together. Okay. And so to solve this, I'll set up an augmented matrix. We're going to have 7 columns and 6 rows. The rows represent the equations. And the columns represent the variables in whatever order you want to do. I'm going to do F12x, F12y, alpha 1, A2x, A2y, and alpha 2, and then the last one is the constants. And then I've already written all these equations with the variables on the left and the constants on the right. And so now all I have to do is go through these equations and read off the coefficients and put those in the matrix. So F12, so let's see, I have it written here. F12x for the first equation, that's negative 0.7071. F12y, positive 0.7071. Alpha 1, negative 1.6 repeating. and the constant is negative 53.37. Equation 2, f12x is negative 1, a2x is negative 5, 0 for the constant and everything else. Equation 3, f12y is negative 1, a2y is negative 5, and the constant is positive 49.05. Equation 4, f12x is negative 0.3535. F12y is negative 0.3535. Alpha 2 is negative 0.416, repeating. The constant is 0. Equation 5, alpha 1 is negative 0.7071. A2x is negative 1. Alpha 2 is negative 0.3535. And the constant is 35.35. And then equation 6, alpha 1 is 0.7071. A2y is negative 1. Alpha 2 is negative 0.3535. And the constant is 106.06. And then reduced row echelon form gives you F12 is 72.51, 92.03, and that's newtons. Alpha 1 is 40.30 radians per second squared. The acceleration of the center of mass of 2 is negative 14.50, negative 28.22. And the angular acceleration of 2 is negative 139.59. Any questions about the calculations or anything? Okay, so let's interpret what we have. This is, I think, cool. So what we figured out is, if this was a static case, you know how to calculate the reaction forces. But we figured out that with this thing moving that way and with this force applied, what the contact force is between member 1 and member 2. Okay? There's nothing about the combination of the weight and the force applied here or anything like that that would let you get like an intuitive idea of what that contact force is going to be. But we figured it out, And if this was a biomechanics problem, if this was something that, say this was something that happened in a car accident a lot, like you knew that the knee hit the dashboard with this much force, we could use this calculation to figure out what kind of forces the ligaments are under, what we could change to make it less dangerous, that kind of thing. And then the second thing we figured out has to do with the motion that results. We didn't, we don't calculate anything about the angular velocities because that doesn't have to do with the forces applied at that instant. Only the accelerations are determined by the forces. But we figured out that body 1 has a counterclockwise angular acceleration, and body 2 has a clockwise angular acceleration that's quite a bit bigger in magnitude. So let's think about what that says. Okay, so this force is going to make body 1 have an angular acceleration this way, right? Counterclockwise. The direction makes sense with the force. But what isn't so obvious, and what we figured out, is that the angular acceleration of 2, which also is clockwise, and that the direction makes sense, but we get a much bigger angular acceleration of body 2 snapping that way from this force than we do of body 1 snapping that way. You get this sort of like whiplash effect. So this is a really simple linkage problem. You know, you can't make them much simpler than this. And that part's a little disheartening because it took us 2 classes to do this. But the cool thing is, I mean, without changing any of the technique, you can imagine how you could apply this idea to like any kind of multi-component machine. If you're going to get more than a small number of members, it wouldn't be practical to do it by hand. But it's a very algorithmic sort of approach. You know, it's not too much of a stretch to imagine that for whatever your application is, you could write a pretty simple program, as computer programs go, to do this calculation for you. You know, and then we calculated this at a single instant. Well, we know something about the accelerations of these points. What if we wanted to know what happened over the next 10 seconds or something? Well, as long as we know the forces at each of those instants, we calculate these accelerations. You can integrate those numerically. You know, your program can just do the integration over time, calculate what the angular velocities are at the next instant, and then use all that stuff as inputs for the next instant calculation. You know, run this through your program. This is all a loop. You know, by hand it takes forever, but on a computer this loop is instantaneous. Calculate it at 0.01 seconds later, figure out what the accelerations are, integrate again, go to 0.02 seconds later. And doing that, you can actually do simulations of what happens over the whole process. Yeah. Yes. Yeah. Right. And so like when I give this to you on tests, what I often do is I'll just say, give me the, like, don't solve anything, just give me the constraint equations for this one joint, you know, or draw the free body diagrams of the different things and then write out the constraint equations. So that, because otherwise, even to do like the simplest problem would make you work sort of fast in a 50-minute test, you know, so there's not much I can do there. But any questions about that one? Yes. Yeah, the way to do it is for each body, this one has 2, you know, but each body in the linkage, use Newton's laws, you know, go through the rigid body problem steps. So if there's a fixed point, you don't use Newton's second law. If there's no fixed point, you do. Get all the equations from Newton's laws. Every body with a fixed point, it'll give you 1 useful equation. Every body with no fixed point will give you 3 useful equations. So list those all out. And then when you're done with that, you'll have more variables than equations, okay? And the difference there will be the number of constraints you can get from the joints connecting bodies. And then you just go to the joints. And then, you know, different joints put different restrictions on the motion. A pin joint always just says the accelerations have to be the same at that point. And when you go through those, you'll finally have a system with the same number of variables as equations, and you can solve it with reduced row echelon form. Any other questions? Okay. Let me show you the next example, the last example I want to do. And then I'd be happy to, when you guys start having questions about homework problems, I think I'm not even going to start this today, but let me just talk about it for a second. So the next example, we have a pin joint there connected to a rod, and then that rod is connected to this one by a pin joint. And this second one, it's not connected to the ground by a pin joint. That would be a structure. It wouldn't be able to accelerate. Instead, this can move freely in a slot. And we'll say at this instant, this angle 60 degrees, this angle 60 degrees, so it's an equilateral triangle. I'll call this body 1 and body 2. And we'll say that the length of 1 and the length of 2 are both 3 meters. And the masses are both 10 kilograms. And at this instant, both of these two members are at rest. So the angular velocities are 0. So it's starting from rest, and then we're applying this 600 Newton force this way. And I'm going to call these joints, this one A, B, and this one C. And for this problem, let's say that instead of just generally figuring out the angular accelerations of the bodies, we want to figure out specifically what's the acceleration of that point C, that pin C in the slot. Like if this was, why would we want that? If this was part of what's that called on old style railroad cars that turns the wheels, the crankshaft? You know what I mean? This thing moves around and turns the wheels in old timey movies. So say that this was connected to, somehow connected to like a gear or something that's turning the wheel. And we want to be able to calculate at this instant what the acceleration of that point. So we want to calculate what's the acceleration of the pin in the slot at C at that instant. Okay, well, let's just sort of look at this and see if we can figure out how many variables, how many constraint equations we're going to get. Okay, so first member 1. How many useful equations are we going to get out of member 1? Just 1, because there's a fixed point. And for variables, we're going to have, so there's a reaction force here, but just like the reaction forces at the fixed points never appear in our initial system of equations, just like it didn't last time. And so the variables we get in this one equation for body 1 are the force on 1/2 at this pin. So that's 2 variables.
and then the angular acceleration of that body. So 3 variables in that one equation. Okay. So we're behind by 2 so far. And then we go to the second one. How many equations are we going to get? 3. There's no fixed point. It's as simple as that for figuring out, even though there's some more complicated stuff going on here. So now we have a total of 4 equations. What variables are we going to introduce? Well, just like before, we're going to introduce the acceleration of the center of mass and the angular acceleration. Okay, so that's 3 more variables. Okay, so that would be 6 variables. But now we have one more. This pin and slot joint applies a vertical force, like a normal force, to that pin, right? And so that the magnitude of that force, we'll call that n or something, is a 7th variable. Okay. All right, so we have 4 equations and 7 variables. So in this case, it looks like we actually need 3 constraint equations, not 2. Okay, is that going to be a problem? It's not, because we're going to have the 2 constraint equations here, just like we did in the last one. But we're also now notice that this pin is confined to only accelerate in the y direction. So our 7th equation is we're going to come up with an expression for the acceleration of that point C. And then we're going to say that the x component of that acceleration is equal to 0. Okay? And so we'll get 2 constraint equations here, 1 more here. We'll have a system of 7 equations and 7 variables. So it's cool how it works. I mean, if this wasn't here at all, that wasn't connected to anything, you know, this was just out in space, we just basically have a sideways version of the problem we just did. But if you add a, you know, another joint, another requirement for the motion, it adds more variables because there are forces at that joint, but it also adds more constraint equations that are available to you, and they always match up. Question? Yeah, to calculate the acceleration of this, we'll have to use relative motion and say, you know, AC relative to ground is equal to AC is equal to AC relative to the center of mass plus A center of mass relative to the ground. Yep.
Are we assuming that C is frictionless?
Yeah, in this case. It doesn't change the sort of approach at all, though. So, like, for example, let's say that there was viscous friction in there, you know, that it's full of oil or something. And well, the force that's applied by the oil to this thing is proportional to how fast that's moving. So we just come up with an expression for how fast this is moving based on the angular velocities. I guess the way it's set up right now would be 0. And then we just put that in as another force. Since we already know the angular velocities, it would just show up as a number. You know. Same thing here, like if you wanted to include some friction there, you might just include that as like a moment on each one of those, you know, a small little extra moment. And if you knew that as a number, you just add that in and it doesn't change the process at all. Any other questions? Okay, that's it. Have a good weekend.